Hello, this is the sixth video in the series of ship stability. In this video we will be talking about the metacenter. It's the last method that was described previously. In this method we're going to use a measuring point that was invented by Pierre Auger, and the reason that he had to invent it is because he was using a method that today we don't use. We use more sophisticated, and that's part of the archaic part that was left in this analysis. And strangely it stayed for over 300 years and it wasn't moved. Pierre Boutger was very smart guy. In fact, maybe that's the reason that it was so entrenched, that he was considered to be one of the smartest guy. He beat Euler in some math competition. He become professor at age 15. In this method, when we're tilting a body, let's say an angle theta, the buoyancy center move from point B to B prime, and then if we move a line that will go from B prime in angle of theta to the center line, that will bring us to point M, is the intersection of this line with the vertical line that we have here. If we do the geometric calculation correctly, we're going to get the GM equal to the ratio of moment of inertia divided by the immersed volume minus the distance between B and G. If we're going to do example how we're going to use it, we take our favorite extruded rectangle, which have width of B, height of big D, and the part that it's immersed is little d, and the length of this thing is S. And the moment of inertia, it's SB divided by 12. The immersed volume, it will be little d times SB, and G is big D divided by 2. It will be in the middle of the whole thing because we have uniform material, and little b, it will be the middle of the immersed part. And the solution for this kind of thing is presented here. If we draw this kind of thing, we can see that in that case, let's take the simple case. If the width equal to the height, we can see that from the experiment that we have, if we have middle density, it will be unstable. If we have low density, it will be stable. And if you have high density, stable. The only thing we can clearly see that if it's very low density ratio, it will be much more stable, or GM will be larger as opposed to the high density ratio. This configuration, this presentation, it was invented by me, and I believe that's encompass a lot of information. For example, if we look on the ship of the famous ship that blocked the Suez Canal, Ever Giving, and that ship was basically 60 by 60 meter with length of 400 meter. If we look on the ship, it will be ratio of 1, and the density, what I check it out, it's about 25 or so it's about 0.4. It's very unstable. So it means they must have to move G lower, and indirectly they have to move extra load around the world to move the ship. Okay, let me summarize what we've done today. We explained what is GM, we explained the method, we present a simple example of extruded rectangle, and we show that the solution can be presented in non-dimensional form, which encompasses a lot of information in a very short presentation. And then we can look on the physics of this situation and explain it when the body can be stable or unstable. Thank you very much for listening to the explanation in this lecture. Please click like and subscribe to the channel. Thank you and have a nice day.